Welcome to Module 3, where we are looking at the effect of shape on material selection, process selection, and functional changes that occur in a design. We had at the outset reinforced the concept that material function, process, and shape are interrelated. During this module, we'll look at different aspects of shape that get included in a design and how that can be accounted for numerically by introducing the idea of shape factors, microscale shape factors, how material indices are modified to include shape related attributes at multi-scale, and how that will allow us to jointly select for a given design material and shape options that would be best suited and would be the most efficient. Now, the idea of shape affecting function is not new. Curvature of lenses and mirrors, so that you're dealing with optical properties, fins in a heat exchanger, so thermal properties, a piece of marble as opposed to a sculpture embedded inside that needs to be chiseled away by the artist, so aesthetic attributes, energy storage, capacitance. So these are all some possibilities. We will in particular look at the transformation of a material into a given shape from mechanical attributes during this module. And by shape, we are looking at tubes, ice sections, hollow box sections, sandwich panels, rib panels, and such. When we are talking about the term efficient, we want to use the least material to achieve a given stiffness or be able to support a certain strength in a design. The shapes that can be generated from a material or a process have certain inherent limitations, and so that can limit, as you might imagine, the extent to which the combination of a material or a shape or a process can deliver on a function. So what we are talking about is that these shape efficiency factors that we want to introduce are going to have an upper bound for various processes and materials. Let's build off from that. If you look at table 9.2 in your textbook, you will come to some version of this where a number of different shapes that are commonly available in designs and various attributes, including the area for a given shape, that is the cross-sectional area, and various moments, area moment I, moment Z, moment K for torsion, moment Q, and so on. Okay. So, for instance, we saw that the area moment is BH square by 12, BH cubed by 12, sorry, for a rectangular cross section. So going from table 9.2, one thing that has to be reinforced that we knew from strength of materials classes is the fact that in addition to the shape, so the loading matters as well. And so for certain loading conditions, certain shapes are more efficient than others, which is introduced in this case for a tensile geometry for a tie as opposed to a column which is under compressive strength in the bottom, and things related to bending or torsion in the middle. So different geometries work better in different loadings, just like different geometries work better with different types of materials and processes. So the goals of this module is how to compare between various options that include material and shape considerations for a given design. And so, focusing on mechanical properties, we look at a stiffness limited design as well as a strength limited design. And we look at how material substitution can be achieved at constant stiffness or strength, but allowing for differences in shapes. For this, we will introduce the concept of shape factor. And given that shapes not only depend upon material aspects, but also on the loading. Let's look at stiffness limited designs in bending loading. In order to be able to compare the effectiveness or the efficiency of utilizing a material for any given shapes as alternatives, let us look at the ratio of the bending stiffness S of any new shaped section on the right to a reference section, in this case a square cross-sectional area B, right, of length B. In this case, for the reference area moment is B to the power 4 divided by 12, or since the cross-sectional area is B square, it can be represented as A square by 12. If now we keep the area constant and change the shape, the area moment, of course, can be determined by this integral. We define shape factor as noted above as the ratio of the bending stiffness S for this new shape, which is the product of the modulus E times area moment I, to the reference stiffness for the cross section, square cross section, which is E times I naught. If you rearrange terms here and introduce the amount for I naught, then for the same material, the modulus will be the same, and you have the shape factor then as 12 times I divided by A square, where I is the area moment for the new shape, and A square is the cross-sectional area for any of the shapes. If you look at table 9.3, there are a number of shapes for which under a stiffness limited design or a strength limited design, you have different kinds of shape factors associated under those two constraints. So we are talking about being able to account for changing the material, say going from an aluminum to steel, in addition to the reference loading situation, maybe a new material that could be better used. Material substitution at constant stiffness or strength, but allowing for differences in shape. So that is one type of an approach that is afforded by these shape efficiency factors. And the goal is to understand the limits to shape and develop methods for co-selecting material and shape. How do we use this information would be the ultimate goal. For this class, let's look at how do we arrive at these kinds of for these common shapes. How do we arrive at these various shape efficiency factors?